So, last class we talked about basic memory circuits, something that would build and become a block of memory. And all the types of memory that we talked about, whether synchronous or asynchronous, had K address lines, N data lines, N data outlines, and then some number of control signals. That's just the control interface that we care about. Common control signals that you'll see: read, write, output enable, which is what you would use if you wanted to read from something, write enable, which is what you would do if you wanted to write something. So these are sort of mutually exclusive. Okay, two ways to do the same thing: output enable, write enable. We would also maybe sometimes just see a generic enable or a chip select. And these could be active high, active low. Probably most of them are active low. But that controls how we read or write. We talked about different ways of addressing individual bits. We talked about that bit cell, okay, with its data output, its data input, its select, and its read-write lines. Today, we're going to talk about something a little different. Types of memory. Because aside from the fact that they store bits, there are lots of different types of memory that have nothing to do with each other. And we basically are going to split this up into two types of memory. One is called ROM. The other is called RAM. ROM stands for read-only memory. RAM stands for random access memory. These are the two big categories of memory that we're going to be using in any system for the rest of your career here at UMass Dartmouth, and in your career in the world. ROM stands for read-only memory, which is actually a bit of a misnomer, because if you could only read from a piece of paper, for example, I grab a piece of paper and I read off of it, what starts on that piece of paper? Nothing starts on it. So read-only memory is actually write once memory. You write to it once, and then you can never change it. So I suppose you could call it ROM memory, but that's difficult to say, so we don't do that. It's called ROM, read-only memory. RAM, by contrast, is both read and write accessible. Everything we talked about last class was RAM, read and write accessible. Now, without going into too much detail on types of ROM, here's your basic ROM setup. Not the only way, but this would be maybe a mask ROM. Mask ROM is written once at a factory, and it consists of K address lines, and then 2 to the K decoding of it. And this is sort of internal here. That's your external interface on the left. This is internally what happens. And then we're going to use the same setup I used last class with that bus tap OR, just to indicate what's going on here. That's right, I have my cool straight lines. It only took me 3 semesters to learn how to draw a straight line. So we've got these 8 lines here. So I'm pretending that this is a 3-bit address. So I've got 8 output lines of this decoder. And I've drawn the decoded outputs as red lines. And right now, nothing's connected. We just have these OR gates. So with nothing connected, we see a 0 on all of these, right? Nothing is connected. To program this, we'll actually go ahead and we'll take and we will connect up selectively for using a process in silicon, okay, some of these connections. So I have just connected these. Now, when I put a particular address in, let's, for the sake of argument, say I put in an address of 3. That would be a 0, 1, 1, 3 to 8 decoder. Which one of these lines will be activated? Well, it would be the 3rd line. So this is line 0, 1, 2, 3. This line is, oh, that's a terrible, well, that's okay, that's a start. So this line is activated. It's driven high. It sees a 1. Now, is it connected at any of these 4 points? No, it's not. So the only thing this sees is a bunch of zeros. So as a result, what do we get out of that? We get 0, 0, 0, 0. That corresponds to what is stored at location 3. Let's do something a little more interesting. Let's look at location 2. Put a 2 into the address line. That means now this line is activated. And as a result, these points right here are connected. So I will see a 1 coming out of these 2 OR gates. Here we're not connected, so I'll still see a 0. So at location 2, I have stored the number C. Now, the simplest way to think about this on a macro scale is imagine we have a bunch of wires, but they have insulation on them, right? If you put 2 wires that cross each other with insulation, we don't have a short. It's protected. That's the whole point of insulation. It insulates. Now imagine I take a laser cutter. I take a laser cutter and I fire right at that cross. That's going to melt the insulation on both, at which point now they're touching, right? That's effectively what's happening, although it's a different process. It's not a laser that's melting insulation. But in a mass grom, that's kind of how that works. That's all there is to a mass grom. Big decoder, and then a grid where you can selectively set bits to be 1. So if I gave you that same grid, or well, the grid, where's my line here? Gave you a grid. Here we're going to try and get crafty. Take both of those, Control C, Control V. Okay, 8 lines that way. And then also our 4 output bits. If I wanted to fill this with, let's call it a binary counting sequence. 0, 1, 2, 3, 4, 5, 6, 7. If that's what I wanted to store in this memory, okay, each one of the yellow lines represents an address in this ROM. So if I wanted to store a 0, all that is required is for me to not connect any of these, because the binary value of 0 is 0, 0, 0, 0. So I don't connect anything. If I want a 0, don't connect it at that yellow line. For 1, I do want that to be connected as a 0, 0, 0, 1. So I would make a connection there. For 2, I'd make a connection here. For 3, I'd make both connections. For 4, connection like that. For 5, for 6, and finally for 7. Now, the reason they call this a mask ROM is because when they actually program this at the factory, they create it's not a sheet of metal, but they picture a sheet of metal with a bunch of holes cut in it. Then they shine something through that causes these connections to be made. So they have to make a mask. And once you make that mask is going to go on all of your chips. So if you want to program a new chip or with new firmware, let's say this instead of numbers was actually instructions in a program memory, you'd have to create a whole new mask. And that can be expensive. But if you're making a bajillion of these things, mask is the easiest way. Put the mask over it, shine some light on it, next chip, over and over and over. It's great for high volume manufacturing. Okay. There are other ways to do ROMs, okay? But that's really the fun one, the mask ROM, how to build up a mask ROM. And always over here, this is your decoder. RAMs are a little bit more interesting. Let's see if I can do this. Here we go. All of you guys who are just looking at your like art is happening right in front of you. Ba-ram-you. What is that? That's a fairy tale? Ba-ram-you? Okay. Anyway, no, I've seen Willow. I just don't remember Ba-ram-you being. I mean, she starts off as a ram. She becomes a tie. Anyway, we're getting a little off track. RAMs. RAMs are different types of random access memory. Now, the difference between RAM and ROM, the most important one, is that they're volatile. What does volatile mean? They're explosive. So explosive in this context means subject to state change. Subject to change. Volatile means it's very easy for it to go from, say, a solid to a vapor or fire or bad, boom. Volatile in the case of RAM means if you lose power, you lose data. So the data that's stored on a RAM is volatile, meaning if you accidentally lose power, even if your power dips below the voltage rail for too long, all of the data stored in that RAM is suddenly gone. Unlike ROMs, once you laser etch this thing, it's not going to become unlaser etched. You can't magically put insulation back on. And while we're on the topic, let's say that I've created this mask and then I ship this product out. It's got instructions in it. It is impossible to remove this dot, but it is more possible, not easy, but it is more possible to add another dot. Because you can always, you go back to that laser etching example, you can always go in with a laser and write off another piece of insulation. So it is possible to change memory on a ROM with the right equipment, but you can never unerase a bit that has been set, which is something, it's an interesting security concern. Because if this was a condition, so let's say you're writing some C code and that goes into your mask ROM, and right here, this is where you say, if password is equal to correct password. Well, if you could put a bit here and suddenly change it to not equal, then you've just changed the flow of code, right? You've said now, instead of if the password is correct, you said if the password isn't correct. Suddenly now you can get access. So this is a type of exploit where you go in and change memory. which can be fun, but it usually involves things like fuming nitric acid and no fun. But RAM, a little bit different. It's volatile, and we have lots of different technologies for storing a bit, and we've actually seen a few of them. We can store a bit worth of data in a flip-flop. That's what we did first. When we did last class, we did a collection of registers. Registers are built up of flip-flops. We can also do it with latches. And we did that within our bit cell. Right? This was our bit cell that we added some circuitry around. So one of these is what we would call a synchronous, and the other is asynchronous. There are even more ways to store data. My favorite way of storing data in terms of, I'll put this, in terms of how interesting things are, is a capacitor. A capacitor can be thought of as a data storage. I'm not going to build the full DRAM circuit here, but assume that this is your input. If I put 5 volts here, that capacitor is going to charge up, and eventually I will have 5 volts across that capacitor. If I then remove that input, that 5 volts stays on the capacitor, right? There's no place for current to flow, except this is a physics capacitor, right? Yeah, physics, it's a perfect capacitor. It's just 2 plates. Real capacitors, they tend to have, equivalent series resistance, probably a leakage resistance, maybe some inductive stuff, a lot of stuff going on in a real capacitor. Anyone ever hear of the one about the chicken farmer? Well, chicken farmer's having a problem with his flock. And he went to his friend, very smart guy, physicist, said, I'm having this problem. Can you help me? The physicist said, oh, look at it. He goes down, he checks out, he takes lots of notes, and he goes back to his lab, does math, does science, comes back to him, he says, well, I've got a solution, but it only works for spherical frictionless chickens. Yeah, that's really funny. That's really funny, because spherical chickens, first off, imagine that. That's hilarious on its... Why am I explaining humor to you? In physics, never mind. Anyway, so here's... Can't believe I try so hard. I sit alone at home at night and I think of these jokes for you. And okay, here is a basic idea of how this type of RAM works. We've got a transistor. The transistor you can think of as a digitally controlled switch. You don't have to know the math behind a transistor to understand this demonstration, but it's a digitally controlled switch. So you can think of it as a switch that opens and closes. If I put, say, 5 volts in here, it will close the switch. If I put 0 volts in here, it will open the switch. So I put a voltage here, and I can store a single bit of information on this capacitor. However, and this is kind of the rough part, if I leave that piece of data there for too long, what happens? Well, this voltage is going to start to dissipate. So if you think of how a capacitor charges up, it charges up kind of like this, and it'll discharge kind of like that. Looks like a surf wave. So what we have to do for this type of RAM is actually refresh this RAM periodically by reading it. If you read it over and over again. This is not a real DRAM circuit, by the way, a real DRAM cell. But if we refresh it fast enough, we'll put data on it, and then it'll start to dissipate. But then we'll recharge it, And what we'll get is this kind of sawtooth wave. And as long as we keep that above the threshold voltage for a 1, we keep that 1 there. Keeping a 0 there is much easier because we just leave 0. So this is called DRAM, or dynamic RAM. It, by the way, is the type of RAM I was talking about yesterday that has a row address strobe and a column address strobe. The reason it has that is so that it can continually read row after row after row. I don't think in your book they give you a good picture of DRAM, which is unfortunate, but that's okay. So that's DRAM. So we've got mask ROM, we've got static RAM. Oops, go back a page. Anything that uses this is what we call static RAM. Okay. There are many other types of non-volatile memory that I want to talk about. And this is more of a history lesson than it is how to build these different types. So mask ROM, it's got a grid of wires that can kind of get connected. There are other types of ROM that are a little less ROM-y. ROM stands for read-only, or write once, read-only. The farther you get away from that write once, the better it is for you as a programmer. So non-volatile memories don't have to be write once. We have other types of non-volatile. All non-volatile means it doesn't lose its memory when power goes off. So originally we had something called UV-EEPROM. Okay. UV really just means like ultraviolet light. You would get a chip like that, and it would have all the appropriate stuff on it. These might be address pins, these might be data pins, this might be your control lines. But what was interesting about this chip is it would have a little piece of glass on it. And you could, inside that glass, see a little square of shiny stuff, and that was your actual silicon. So on a chip that was maybe 1.5 inches by 0.3 of an inch, really your silicon only took a very small fraction of that. But this window allowed UV light to shine on this. And so you would be able to program this in a special programmer, and then if you wanted to, you could erase the whole thing by putting it under a black light. These suffered from long erase times, because they'd have to sit under that UV light for 15-ish minutes. Now, there's a sort of unofficial rule with UV-EEPROMs. If you want the chip to be erased, it has to sit in the eraser for about 15 minutes. If you don't want it to be erased, putting it in there for even a second will erase the whole chip. So long erase times, but it was quick to program. But it did require a dedicated programmer. So it was supplanted by more technology. So the next type of technology I want to talk about is EEPROM. By the way, UV stood for ultraviolet erasable programmable read-only memory. So you used a special programmer to program it, UV light to erase it, but after that it was read-only. Once you put it in circuit, it was read-only memory. EE was electrically erasable. Electrically erasable. So this chip, similar footprint, no window, but there were special pins on here that you would bring up to something like 15 or 30 volts. So this is a normally 5-volt device, but if you put 15 volts on this device, you could electrically erase it. So it was quick to erase, quick to program, still required a dedicated programmer. And to make matters worse, you need a totally separate programmer to program EEPROM versus UVEPROM. And they were expensive back in the day. The last kind of non-volatile ROM I'm going to talk about today flash ROM. I see some nodding heads. The flash? What's the flash known for? Speed. It's known for speed. Flash ROM is really neat. It is quick to program. It's quick to erase. No special programmer. And this is the real nice thing. No special programmer needed. So inside this chip is some kind of ROM, and the programmer circuit is built in. So it can talk to this ROM and built in. So this is the whole chip, maybe some kind of TQFP flash ROM device, but it's got the programmer built in. Furthermore, unlike the previous types, this was, you could erase the whole chip, and that's it. You had to replace the whole, even if you wanted to change just a single byte, you had to erase the whole chip. This, much more fine-grained erase control. Usually split up into something like pages, and a page would be some block of memory. So you might have 10 address lines, which gives you how many bytes of ROM? 10 address lines. We did this last class. Split up 10. Yeah, 2 to the 0 is 1. A 1 means K, so it's 1K of memory, or 1024 bytes. But what it might do is it might split this 1K up into maybe 8 pages. So if you take 1K and divide it by 8, how big would your page be? Well, the quick way to look at it is 8 is 2 to the 3, which means if you have that 10-bit address, the upper 3, that's what page you're on. That means your lower 7 is how many bytes are in each page. So 2 to the 7, 2, 4, 8, 16, 32, 64, 128 bytes. Okay, so that's something else that's interesting about that. Now, there's a lot of memory segmenting schemes not going to go any deeper into this than the idea that you might have a page of memory. So there would usually be some set of control signals that go to that programming circuit, or writing to certain addresses in a certain sequence, almost like a secret decoder knock, you know. If you write to certain memory locations or read from certain memory locations in a certain order, that activates the programming circuit. Or it might just have an extra interface associated with it. Nowadays, and this would still have, you know, your K address lines, your N data lines. Nowadays, we care a little bit less about having a full address and data bus. We'll typically buy a chip that has some kind of memory in it, and that memory may or may not include some kind of control circuitry, and then we'll have an interface. That interface will be maybe 3 or 4 lines that goes off to some microcontroller, and that microcontroller will just, through some kind of serial communication, a back and forth communication protocol, ask for individual bytes. But inside of this is always going to be some kind of control circuit that we've talked about thus far. All right. That means with that we are not going to have time to talk about FPGAs. I don't feel terribly bad about that, because you're going to get a whole semester of FPGAs and VHDL with another professor in about a year's time. I don't feel bad about it at all. You'll feel bad about it when you get there. But with that, that's the last lecture, right? Today's Friday. Monday of next week, am I misrepresenting what's going on here? Let me load up the syllabus. Syllabus, 260 syllabus. Oh no, on Monday I get to talk about FPGAs. Oh, that'll be fun. That'll be fun, guys. A very high level of what's going on with FPGAs. That'll finish off Chapter 7. But for today, though, I'm going to cut the lecture here. Maybe, if I can figure it out. Cut the lecture here and we'll do reviews. Or, yeah.